Hey everybody, welcome back to another video. Remember back in high school, every class there seemed to be some kid sitting in the back, asleep, head down, snoring the whole class. You ever wonder what happened to those kids? This is what happened to those kids. But today, we're talking about this one. Yep. Miss Mensa has some issues with the way the guy in this video is explaining superconductors. Now, for someone who has a 98th percentile intellect, which is what you need to get into Mensa, she's sure having a pretty difficult time following along, and this stuff isn't that hard, especially for someone as smart as she is. Now, she's made a rebuttal video. She's woven in pedantic questions that only the sleeper in the back of the class would ask. So in doing research for this video, I went to the normal places you'd go if you want to learn something. I asked Google. I searched the Wikipedia page for about 20 minutes. I watched a few, maybe 5 YouTube videos about the topic. And after that time, I have a pretty good understanding of how this works. Now, I'm not saying I'm an expert. I really hope no one thinks that I'm saying I am an expert. But after doing just a minimal amount of research on the topic, trying to learn something about the topic, I have a pretty decent understanding of how it goes. For some reason, she's just not getting it. Maybe she didn't do enough research. Maybe she's just an idiot. I don't know. But in 2020, if you can't come up with enough information to really get an understanding of something, there is no hope for you. Now, for some reason in her video, she sped this guy up a lot, and his voice is very high-pitched and sounds pretty weird. I tried to fix that by adjusting the pitch down, but when I did, it adjusted the length and the speed of the video, and the audio didn't really sync up well. So I spread out, expanded, whatever, her video in an attempt to make him sound a little less, Alvin and the Chipmunks, but he's still pretty high-pitched. It isn't as annoying as it is on her video, thank God, but you're going to have to bear with me on this one. And thankfully, she doesn't even talk throughout the entire video. So that's good, I guess, right? Now, I know some concepts can be rather difficult. Others, though, they shouldn't be that hard to grasp. Some of the questions she's posing here are so bad that it's hard to even understand what she's asking sometimes. So let's get into this. Let's figure out why a woman with a 98th percentile intellect is so damn confused. Maybe we can help her out with something. I don't know.
Weighs 19 grams. Okay, let's see how much everything weighs. So the beaker weighs 97 grams. The magnets on top of it weigh 214 grams. Now let's put the superconductor on and see if it increases weight. Okay, here we go. 234 grams. Take it off. 213 grams. Put it on. 236 grams. So you can see that the weight still increases even though it's levitating on top. Now I can actually set stuff on the superconductor. Let me set my lens cap on here. And you'll see that the weight goes up even more as if I'm just setting it on the scale by itself, 248 grams. So it's as if there is actually a material in between there supporting the weight. So there you go, putting a superconductor on a scale does increase the weight, as if you're just setting it on the scale normally. Okay, so why did the weight increase when we put the superconductor on the scale? Well, that's because even though it's floating and levitating there, the reason it's floating and levitating is because it has a repulsive force from below it.
The magnet under the superconductor is creating a magnetic field. And the way superconductors work when they're very cold is that they repel all magnetic fields. Therefore, it levitates. The reason it stays levitating in the same spot is called quantum locking. That's a concept I'm not even going to get into. No, not gravity.
And so the force is getting translated up into the superconductor. So just like if you have two repelling magnets, if you push on one magnet, it can push the other one away.
Still not gravity.
So imagine this were a scale and this were the superconductor. If the superconductor is going to support itself, it's pushing down. So it has to push down to oppose gravity.
I admit, he could have worded that part a little bit better, but come on, you know what he's saying. Maybe he should have started the video off by saying that superconductors aren't magnetic, they're diamagnetic. Maybe he did and you just cut it off, I don't know. The repulsive force from below is the magnetic field emitted by the magnet.
And that pushing down translates into the scale below.
Pushing down force? What force could that possibly be? So a couple things. The superconductor isn't emitting a force. It's repelling against magnetism. And there's more than one force at work here. Gravity pulls down on the superconductor, right? Giving it weight. The magnet underneath the superconductor is pushing up on the superconductor, making it levitate. And the weight of the superconductor is added to the mass and the weight of the magnet and the beaker, thus increasing the weight on the scale.
Even though it's levitating there, it's still pushing below it. So it's almost as if the superconductor is just in contact with the scale. There's nothing special going on.
What force?
So even though it's levitating there, it's still pushing below it. So it's almost as if the superconductor is just in contact with the scale. There's nothing special going on.
Now she really didn't understand this part because she had him repeat himself. What pushing down force do you think it is? Use your brain, woman.
Any force that's going on with the superconductor gets translated below. In fact, even when I just set the superconductor by itself when it's not cold on a scale, the superconductor isn't touching anything on the scale. It's actually the repulsive forces of the electrons in the scale and the superconductor pushing against each other.
Yep, that's what he said. What? If you hold a beaker over a scale? Are you serious? You do know that scales only work when you put objects on the scale, right? Have you ever used a scale? What the hell did that mean? Hold on. So you don't know why the beaker not being on the scale would result in a 0-gram measurement? Have you ever used a scale before?
Same thing as with a normal object. When you set something there, it's the electrical repulsive forces of the electrons in both materials pushing against each other.
Superconductors repel all magnetic forces.
So when it's cold, it's actually just replacing that electric force that normally repels it.
Why are you having such a hard time with this? Haven't you ever heard that when you sit on a chair, your butt isn't actually touching the chair? Just like he said in the video, the electrons in your butt and the electrons in the chair are repelling each other. It's just such a minute distance. And it feels like you're sitting there, but that's just the electrons in the chair repelling your butt from the chair. This isn't that hard. And the fact that you don't understand it is kind of expected, I guess.
With a magnetic force. So in both cases, there's this force that acts at a distance, repelling and pushing on the scale.
Nah, I still don't think you get it. The superconductor is up here, right? So then you have a magnet. Superconductors repel magnetic forces. They're called diamagnetics, right? Or diamagnetic forces. So you've got the superconductor levitating above the magnet, right? Because it's repelling above the magnet. The magnet's pushing, the diamagnetic superconductor's pushing down. That makes it levitate. Well, the superconductor has mass. And since gravity is a thing, it has weight, right? Measured in grams in the video. The magnet also has mass. And thanks to gravity again, it has a weight. So those two together weigh something. It's sitting on a beaker on a scale that also has mass. Lo and behold, because of gravity, has weight. All three of those together on the scale weigh what it weighs in the video. If that's not what you're asking, I don't even know. Because, like I said, some of these questions are the dumbest questions I've ever read. It's literally the kid in the back who's been asleep the whole class waking up and being like, well, what force is this? Go back to sleep.
So the only frictionless motion that you're going to get with a superconductor is internally inside of it with the electrons moving inside.
Yeah, he's really going to start losing you now. I think it's best if you just put your head back down and take a little nap.
So a current can go frictionless in there, but the superconductor itself can't move frictionless in the environment.
I wouldn't look at it so much as a pushing down force as more of just a universal magnetic repelling force. Yeah, for the superconductor to be diamagnetic, it has to be super cold. Like really, really cold, liquid helium temperatures. So when it's not super cold, it's not superconducting. Therefore, it's just another piece of material. Is it explained in the video? Not to that detail, but I'm sure the guy didn't expect you to need superconductors for dummies in the first grade level explanation. There are other sources out there that you can turn to learn a little bit more about superconductors, and then rewatch this video, and you'll have a much better understanding of what he's talking about. You might even be able to follow along.
So I hope this answers some of your questions.
Yeah, just go back to sleep. Well, there you have it, folks. What do you think? Did she get it? I don't think so either. I don't think she has any hope of ever understanding things like this. If you've watched any of her videos, listen to what she actually says, you probably understand what I'm talking about. She doesn't come across as the brightest light bulb in the box. And remember, just putting Mensa in your name, or just saying that you're a high IQ skeptic who does high IQ research, calling everybody clowns and idiots, doesn't make you smart. Anyway, if you've liked the video and you'd like to see more of them, give the video a like, give the channel a subscribe. I do appreciate it immensely. And make sure you come back next time. And as always, stay safe out there, people. It's crazy, crazy times.